organic chemistry and functional groups is to think about them almost as like modifications. And what I mean by that is, let's imagine that, or here's my parallel. I hope you can follow. Um, every everyone in the world has an alkane. So that's a hydrocarbon. So that's your base level organic compound. That's just carbon and hydrogen. A functional group would be like so our base level hydrocarbon is kind of like everyone has a Ford, let's see, Taurus. I don't know that that exists anymore. Everyone has like a, a kind of bland or a Toyota Camry. It's just a car. It's a nice car. Camry's a nice car and everything like that. But some people are like, you know what? I want my car to look cool. So I'm going to get flames painted on the side of it because everyone knows that if you get flames painted on the side of your car, it's immediately cooler than any other car. Now, with that in mind, that's kind of like organic chemistry because we have all these modifications, these tweaks, these flames that are painted on the side of the car, but we refer to them as functional groups. So that's what we're going to get after today. Um, we've got a couple of poll questions that we're going to have. Um, I've got three quizzes that are up today. They close on Sunday at 11 p.m. I've got two assignments that are due Sunday at 11 p.m. Um, and then let's see, did I have any other? I don't think I had any other considerable announcements or anything like that. If something comes up, feel free to add it to the chat or, you know, you can unmute yourself and ask and everything like that. I'm hoping to have a practice exam up by the end of this week so that you have a sense of like what sort of questions I'll ask, how I'll ask them, um, and basically kind of a prototype of your exam of this same content that we'll cover. So, um, with that in mind, am I recording? I am recording. I'm sharing my screen, so I'm going to go ahead and jump in. Functional groups. So, functional groups, where do we start? What I want you to know is what are the different functional groups and what do they look like? So the functional groups that we'll get after and that we'll touch on for this class will be addressed today and Wednesday. I don't think that I'll be introducing any more because these are going to be the ones that are essential and needed for the entire class. Um, Functional groups, when you hear that phrase function or functional, I want you to hear function. These do something, they serve a purpose, they help the molecule do something, whether it's make or break a bond. That's the role that they play. Um, there's many more functional groups than we'll talk about. But for what we need, this is going to kind of scratch the itch. Then we're going to look at kind of how they are displayed, what they look like in a molecule. So with that said, there's a couple of functional groups that we've talked about and a couple of classes of things that we've talked about. We know alkanes. Alkanes are molecules that have just, well, a single or a series of single bonds. There's no double bonds, there's no triple bonds. Alkenes are a class of compounds that have at least one double bond. Alkynes, Alkynes, they have at least one triple bond. Can your alkenes have more than one double bond? Absolutely. Can alkynes have more than one triple bond? Absolutely. Um, Nomenclature or organic chemistry nomenclature gets really complicated whenever you have multiple functional groups, but that's where we come into this sort of like ranking. For example, if you had a molecule that had a double bond and a triple bond, well, then that molecule's name would probably end with YNE, just because the triple bond kind of takes precedence. And the reason that I said probably is because whenever you have that compound, it might have a common name that's maybe more important or more relevant. Um, but these are the three that we know: alkanes, alkenes, and alkynes. Now, we've also looked at a little bit esters, thiols, and alcohols. Now, a term that I want you to be very familiar with and comfortable with is polar. I want you to know what polar versus non-polar is. Now, polar kind of means that there's electron density, or I'll just say electrons kind of clustered in one place, or in, I'll say, an area. Non-polar, electrons are not clustered. So if something's not clustered, they're kind of spread out. Now, I've got a couple of Zoom questions. First question goes back a tad. And this one, I think we'll move through kind of quickly, but let's go ahead and get this one answered. I think we can probably knock this one out. Everyone gets this one right. At least one double bond. That's what we're looking for. I'll give about 10 more seconds, or we'll get to 32 people, whichever comes first. Right, there's our 10 seconds. I'm going to go ahead and end the poll. Share the results. 61% of you selected the right answer, and that was ENE. So at least one double bond. That's what we're looking for an alkene, ENE. I know that some of you might have seen this with that one and thought, single bonds, done. No, it is ENE. So I'll stop my share there. And with that in mind, kind of anticipating what you're going to see on your exams, you might see questions like this that just ask you explicitly, what's the definition? So another good example of that, a little bit of a review question. Which prefix is appropriate for a hydrocarbon with six carbons? With six carbons. I think we're going to get 100% accuracy on this one. Nope. We're close. We're close. We got 11 people answered correctly, and then we got one that picked the wrong one. Wrong one. That's okay. Two that picked the wrong one. Let's see. I'll give another 10 seconds or so. I'm gonna wrap it up. And scene. Okay, we'll share the results. Pretty much everyone was, or 85% of you were solidly on that one. It is hex. Think of a hexagon. A hexane is a compound that has six carbons and has nothing but single bonds. So you're going to get questions that ask you explicitly, what is the definition of this? And then you're also going to get questions where I show you a molecule and ask you, is this a hexane? Is this a, pentane and everything like that? So anticipate those sorts of questions. Now, the next question that I want to get after, which one of these compounds is a polar compound? I want to give you a little bit of time to think about this one, but I'm going to go ahead and work through it as well. So we're looking for a polar compound. A polar compound has electrons clustered in an area. Okay, so, we've got three different options: an ester, an alcohol, a thiol, or all of them. We want to select the best answer. Now, if you feel comfortable, go ahead and add What is this? Add that to the chat. There's a specific term for that that I've used before. Starts with an L and ends with an own pair. Perfect, a lone pair. So then I'm going to draw another arrow. Is that a lone pair? Add to the chat yes or no or thumbs up or something. Yeah, we got two lone pairs of electrons. Okay. The thiol looks pretty similar to the alcohol, doesn't it? I mean, we've got one difference. Well, two differences. One is the color palette that was selected, but also we got a sulfur there. Sulfur in place of oxygen. Then if we go over to our ester, well, our ester, that kind of looks like the oxygen there with the two lone pairs of electrons. That ester, that oxygen looks like the ester. Um, that oxygen has two lone pairs of electrons. This oxygen has two lone pairs of electrons. So my question is a lone pair, would you consider that, and add to the chat, would you consider a lone pair of electrons to be electrons clustering in one area as opposed to being like shared between two things? And that's a tricky, yes, clustered. Perfect. Yes. So, I'm going to I want to contrast like these electrons right here versus these electrons right here. Okay, I'm going to label it B and A. The electrons that I've labeled A are evenly shared or pretty evenly shared between oxygen and hydrogen. So would I say that they are clustered or would I say they are not clustered? I'd say they're not really clustered because those two electrons, well, oxygen has some claim to them, hydrogen has some claim to them. And we can quantify that with our electronegativity calculations. But then if we compare that to B, where are those electrons? What are they attracted to? They are only attracted to the oxygen nucleus. So they're kind of like, it's almost like they're anchored to this oxygen right here. So if we say, okay, that oxygen has a lone pair, it has a second lone pair, it also kind of has one of these two electrons and one of these two electrons. This oxygen has a lot of electrons around it. And so that's where you could say that yes, these electrons are clustered around that oxygen. Same thing with the thiol. Same thing with the oxygens and the ester. So which one of these is a polar molecule? All of them. They are all polar because they all have these kind of electron clusters. So the answers that we got, we're getting there. Two more responses. And I'm going to go ahead and call it right there at 4 minutes. 61% of the class said it was all of them. Esters, alcohols, and thiols. There are a couple of people who answered for each one of those. And I'm guessing that if they had this question again, they'd probably answer all of them. Not only because we've said that, but I've given a little bit more of a definition of what a polar molecule looks like. So what I want you to think is anytime that you see a lone pair of electrons, that's a pretty good indication that you're dealing with a polar compound. So I want you to think like lone pair of electrons, polar, just to kind of like help you gravitate that direction. All right. Now, so those are some of the compounds that we've talked about and the functional groups that we've looked at and talked about. Now I want to add a little bit of a wrinkle to those functional groups before we get into some of these other ones. And the reason that I want to do that is because, well, some of these compounds, or the functional groups that we're going to introduce are kind of, what's the word? What's the word there? They can exhibit this. So this phenomenon right here, isomerism. Okay. Isomerism is, well, another way to put it is you have compounds that are isomers. Essentially, what that means is that if you have two compounds that are isomers, does anyone know what the prefix ISO means? Add it to the chat if you do. isolated or alone. Those are both, I like those. Another place in singular or self or the same. So isolated, and I like that thinking of isolated because, you're in one place. You are by yourself. You are in the same location as yourself. So when we talk about an isomer, we're talking about basically two compounds. Let me write this out. I'll write it here. Isomer. Two compounds that are the same, or they have the same formula, but are arranged differently. Okay, so that's kind of a complicated concept. Um, but let's say that, if anyone's ever lived in a dorm, um, your dorm has a couple of things. Like when you show up to that dorm, they're like, here's your bed, here's your bookshelf, here's your desk, here's your chair. You've got like those four things. And you might say, okay, well, I want my bed to be underneath my window. So I'm going to turn my bed to the left. This is turn to the right, whatever. And then you go next door. What is in that person's room? Well, they start out with the exact same thing. Why the slide said alkenes do only alkenes? That's a fantastic question. I'm going to get to that in just a second, okay? Thank you very much for that. I love that question. Um, if you go from your dorm where you've arranged your furniture in one way, and then you go to the next dorm, you're going to see furniture arranged in a different way. You have the exact same parts, but they're just arranged differently. And of course, as the semester goes on, things change. You get a refrigerator, you get this, you get that. But basically, the same parts are just organized differently. So, Alex's question, could you explain why the slide said alkenes? Do only alkenes have isomers? That's a fantastic question because of the fact that in this particular type of isomerism, so there are this, what is known as cis trans isomerism. Let's look at these two. Cis, this is cis 2 butene. And if we break this name down, ENE, we got a double bond. BUT, we got four carbons. Two, well, that's the placement of our double bond. Then cis, okay, cis means same. Well, what this ultimately means when we dissect that name is that shows that this and this, these two functional groups, these two methyl groups, are on the same side. So and what I mean by that is if we were to use a kind of a plane there, if we were to look basically down this molecule, what's on the top? Well, the methyl groups are on the same side. Now, if we look at trans 2 butene, okay, dissect that name. ENE, we got a double bond. BUT, well, four carbons. So double bond, four carbons. Two is a placement of that double bond. Trans, well, that means they're on the opposite. So this is trans 2 butene because our methyl groups are on opposite sides of the double bond as one another. Now, the question of do only alkenes have isomers? No, they do not. Alkenes are kind of the easiest entry into isomers. This is an example of isomerization, or this is an example of two different isomers. This is an example of your trans 2 or your cis trans isomers. Does that answer your question, Alex? Okay. Okay. Now, with that in mind, what we're doing is we're thinking about where are these two groups? Where is this methyl group? And this methyl group, where are they in comparison to this double bond? That's kind of what we're thinking about. And what we want to do is we want to focus in on this double bond because double bonds prevent rotation of the bonded atoms. Okay? So what that means is if we were to draw, let's say butane, I'm going to draw butane. Looks like a little bit like this. H3C. I'm going to draw kind of, you know, as modeled after butene as I can. CH3. And I'm not drawing all the hydrogens there. But we've got our 4 carbons. This would be butane. Okay. Now, this bond right here that connects 2 of our carbons to one another, it's very flexible. And what that means is that this group can rotate down and basically can spin around. It can rotate. And what that also means is that right now, yes, Chris, you're absolutely right. Alkanes do not have any sort of isomerism. Now, whenever we get into alkynes, I think there might be some level of isomerism. So, Alex, if I can go back, the alkenes are your most common examples where you're going to see isomerism or your cis-trans isomerism. Does the more bonds it have? Oh, Andrea, that's a great question. The more bonds actually makes it less flexible. I always kind of think about it almost like I don't know, if you're, it's like an anchor almost. Like if if you, I'm not a boating person, but if you throw a rope to the dock and you tie your boat off, okay, well, then your boat can swing back and forth like this. But if you throw another rope to the back from the back of the boat to the dock, then all of a sudden your boat can only move a little bit. It has less kind of degrees of freedom are what are commonly used as the terms. So when we think about double, that's a that's another great question. So with a triple bond, you have even less rotation. And so yeah, no rotation there. And there's no quadruple bonds. So yeah, doubles and triples have less flexibility and less rotation. So now what we want to do. So isomerism and specifically cis-trans isomerism. This is where we have groups that are positioned opposite or same. Our butene, we've got, well, they're on the same side of that double bond. Trans, they're on the opposite sides as that double bond. Now, our next, so this is an important phenomenon to understand because what this relates to is that there are some compounds that will have some level of functionality and some drugs, for instance. Um, I think Tylenol is an example. Whenever you take Tylenol, like if you were to go to Germany, I think is one of the countries that I've always heard of. If you took Tylenol in the United States versus Germany, you'd take a 250 milligram pill in the United States and only a 125 because the the version in the United States is going to have 2 isomers, whereas in Germany it's only going to have one of those isomers. So you have less of it, but only one of them does something for you. And so the German version is like, well, it's gotten rid of the stuff that doesn't do anything or it doesn't help you. Okay. Next class of compounds are aromatic compounds. Now, an important point is that aromatic compounds are cyclic. So aromatic compounds are always going to be cyclic. They contain alternating double bonds. And I've got this kind of, I guess it's like well, either a Mickey Mouse or just a shocked look on someone's face. This compound right here is benzene. Now, benzene is, if you were to like try to put this name together, this is the common name for this compound. If you were kind of constructing the name, it's pretty reasonable to say, okay, I've got double bonds, so I'm going to say ENE. Okay, it's an ene. Okay, then I've got 6 carbons, so I'm looking at hex ene. Well, I've got 3 double bonds, so this would be, I'm getting there, Stanley. You're exactly right. It's cyclic. So I would say maybe tri cyclo. Well, no, that's I've got three double bonds, so I would maybe go with triene and then hex O. And I'd also want to add that it's cyclic, so I'd say cyclohexotriene. It's kind of a mouthful, but does that capture everything? It does. It does capture it's got double bonds. I've added the tri to indicate that it's got 3 of them. Hex indicating that it's 6 carbons, and then cyclo indicating that it's cyclic. Now, before I'm going to erase that because that's not the common name that we use. Between compounds A and B, do you notice any differences between A and B there? Double bond placement. You're absolutely right, Chris. Those double bonds are in different places. So we've got dun, dun, dun. And then, well, they're kind of alternating. Now, if you remember, there was one thing that I mentioned last week. I think that it was like, I think it was octene. One, two. I'm going to try to reproduce it. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, this molecule that I just drew has 8 carbons. It's cyclic, and it's got 1 double bond. So I could look at that and say cyclooctene. I make it a triple bond, call it cyclooctine. When we look at this compound, though, one of the things that was important is usually when you have a functional group, like what we did with our butene, we use that 2 to indicate where our double bond was. The 2 said where it was. Well, we didn't do that with the cyclooctene. Why didn't we do that? Well, because who's to say, since there's only one double bond, it doesn't matter if you say that this is carbon 1. That's where it would be in terms of like numbering of the molecule, because that's one of the things that organic chemists are particularly concerned with is which is carbon number 1, which is 2, which is 3, which is 4, and so on. So that's a big part of organic chemistry, numbering your carbons. But I didn't do it with the cyclooctene, and the reason is because, well, if I called this number 1, then this would be number 2. If I called this number 1, this number 2, that's fine. They're both acceptable. The only thing that would be wrong is if I was like, oh, this is carbon 1 right here. That's just straight up wrong because you want to give that double bond the lowest possible number. Just like what we were doing whenever we were naming our compounds. So now with that in mind, let's say that you and a friend were both drawing benzene, and you drew it as A and your friend drew it as B. Who's right? Well, I mean, you'd probably say, "Oh, I'm right." And I'm not saying you would. I'm just saying I would. I'd be like, "I'm right." You're right. It's both though. Both of them are correct. And since both of them are correct, they're both kind of wrong also. So if you look at this figure at the bottom, this one right here, that's how we draw a molecule with alternating double bonds. Because truth be told, benzene doesn't have an aromatic compounds. Yeah, they have alternating double bonds, but those double bonds are never like stuck between here and here. It's not like, well, that's where they are for forever. Instead, these double bonds are what are known as delocalized. And I like to use that term, I like to bring that term out, but I'm not going to be asking you about that term. Instead, what I want you to know is that since those double bonds are delocalized, then a better model for what you need to draw is this one down here with the circle in it. Because that shows that, hey, it's not a double bond stuck like with octene in one specific location. This double bond is never going to be like, oh, I want to go here, or I want to go here. Instead, this, however, with benzene, this double bond is like, well, I've been here, now I'm going to move. And then that forces this double bond to move, which forces this double bond to move. And so there's just this kind of mobility of those double bonds. Starts in one place, but then it goes to the next, and then it goes to the next, and then it goes to the next. That's a fantastic question. And the answer is no, this is unique to cyclic molecules with multiple double bonds, cyclic molecules with alternating double bonds. You wouldn't have that with a or you wouldn't have, or there's not, to my knowledge, any sort of triple bond analogous molecule. It's a fantastic question, though. Now, to capture a couple of these molecules, these aromatic compounds, here they are. We talked about these a little bit because they have odors. Um, they're they have an aroma. Naphthalene, pyridine, orthoxylene. Notice how all of these double bonds are represented, for the most part, as a circle. Um, you could do the same thing with that pyridine and indole, or those two compounds, because they have that same sort of delocalization of electrons. Yeah, we've drawn them here, but they're just as likely here, or just as likely here, or just as likely here, and so on. Now, these compounds, these two right here, pyridine and indole, these are important compounds for molecules like DNA and basically genetics and um, life. But that's, I just want you to know these as being able to identify an aromatic compound and understanding that the electrons, like when you draw a aromatic molecule, what are you going to see? You're going to see alternating double bonds, and there's not one that's more right than the other, and so on. Okay. Could I get a thumbs up or a yes if everyone's good with aromatics and like identifying them and stuff like that? Okay, great. So aromatics are a big part of life, industrial purposes, um, and so that's kind of where they are. And they're basically just cyclic molecules with multiple double bonds. Now, the next class of compounds that I want to talk about are halogenated hydrocarbons. Now, when you think about, or probably when you think about halogens, or what I want you to think about whenever you hear halogens, is I want you to think about the periodic table. And specifically, I want you to think about where the halogens are on the periodic table. They're on the far right. They're non-metals. Now, these are also known as organic halides. These are organic compounds with halogens as substituents. So they have fluorine, chlorine, bromine, or iodine. These are our most common halogens. One example would be 2-iodopropane. Now, for each one of these molecules, I just kind of like to work it backwards. A and E. No double bonds, no triple bonds. Prop, 3 carbons. So we've got 1, 2, 3. Iodo. Okay, so we've got a 3 carbon molecule with nothing but single bonds and an iodine. Then we got a 2 right out here. Well, there is carbon number 2. Now, one of the things that we previously talked about is numbering carbons. This is 2, it's in the middle. It doesn't matter if we start here, 1, 2, 3, or if we start here, 1, 2, 3. Next up is tetrafluoromethane. Okay. Ane, nothing but single bonds. Meth, not Breaking Bad meth, but instead the stem meth. 1 carbon. Where's that carbon? Smack dab in the middle. So there's our methane. Tetrafluoro. Okay, fluoro means we've got fluorine. Tetra means we've got 4 of them. So we've got 4 fluorines around our central carbon. So tetrafluoromethane. And just because this doesn't have any hydrogens doesn't mean that it isn't methane. It's just a organic, or it's a carbon-based molecule with nothing but fluorine surrounding it. Ane, hex, bromo, 2. 2-bromohexane. Okay, we've got a alkane with 6 carbons, a bromine, and it's at position number 2. Now, if we were to take this molecule and redraw it like this, add to the chat how you would name that molecule that I just drew in red. Okay, I like it. Cyclo-2-hexane. Okay. Now, I would say this is a instance where you gave 110%. So you got it and then went a little farther. The only issue with this name is when we're numbering a cyclic molecule, we don't necessarily have numbers, which sounds kind of backwards, but if we were to call this anything, we would probably call it cyclo-1-hexane because we want to give that bromine or cyclo-1-bromohexane because of the fact that we want to give the bromine the lowest possible number. So what we can really do is just call this cyclo-bromohexane. Now, it gets a little bit trickier when we do something like this. I'm going to change colors so then if anyone looks away for a second isn't completely confused. I'm going to add a BR here and then a BR here. So here what we've got is I'm going to start at the end, still ANE, still hex. It's still got bromo. So I'm going to add, it is bromohexane, but how many bromines do we have? Got 3. So I've got to upgrade this, absolutely right, to tri-bromohexane. And in this case, what I'm going to do is I'm going to add a little bit more detail. Because if somebody saw tri-bromohexane, they're thinking, and I haven't added cyclo, but I will. They're thinking, okay, well, it's got 6 carbons, it's got 3 bromines on there. Where are they? I don't know. Well, here we know where they are. So we would say 1, 2, 3 tribromohexane, and then I would go ahead and add that prefix cyclo to indicate that I'm talking about a cyclic molecule. So this molecule that I just drew is cyclo 1,2,3 bromohexane. Now, where another kind of layer of the onion where it can get kind of tricky is when if you look at it and you say, well, which bromine is at position number one? Is it this one? Is it, well, we know that it's going to be 1,2,3, so that's fine. Or 1,2,3. For this and for our class, this is kind of the this is where our barrier is. This is where I say, all right, stop right there. We've added, think about the complexity of what we've just drawn. We've drawn an alkane. Okay, good for surface level. Then we've added the prefix. Okay, so that's the next level where we're applying something unique. We're looking at how many carbons it has. Then we're brominating it. We're looking at a halogenated hydrocarbon. Okay, so that's a next level. Then we're cyclizing it. That's a next level. And then we're looking at where it has three. So then we go even further. So when there's a singular BR, you don't need to specify position. A singular on a cyclical or on a circular, a cyclical molecule. Yes, you're absolutely right. Awesome. Great insight there. Um, okay, so then our next compound, dichloromethane, well, it's two chlorines on basically methane. So in that case, we don't say 1,1 dichloromethane because, well, how many carbons are there in methane? There's one. And so, well, those chlorines are only going to be found on that one carbon. So that part makes that a little bit simpler. Okay, so when you see or think about halogenated hydrocarbons, I think that the four examples here, and then the fifth one that we drew and then modified, those are good sorts of questions to think about with respect to your exam and like nomenclature. But like I said, I'm going to get a practice exam up later this week. Now, last poll question for the day. Can you have a halogenated alkene? And this is really just kind of like, what do you think? You think it's possible? And really, like, based on what we've seen, kind of a, well, why not? Is what I'm getting at there. And I mean, the answer is, yeah, you absolutely can. You can have a halogenated alkyne. It doesn't really matter. Um, because what we have here in terms of like what do you need? You need a carbon and you need a halogen. You need that bromine. So if you have a carbon and bromine, they can form a connection. And then you can have that bond form. And so thank you guys for answering that one. Okay. Next up is a little bit of a deeper level of chlorinated or halogenated hydrocarbons. Chlorinated hydrocarbons. Yes, a chlorinated hydrocarbon is an example of a halogenated hydrocarbon because we're talking about chlorine there. These are slightly polar substances. They do not dissolve well in water, but do dissolve well in fats. Okay, now this is kind of interesting, but let's think about that in terms of polarity. What do we know about um, polarity and electronegativity? What we know is that the most electronegative element, add to the chat if you remember the most electronegative element. I'll give you a hint, far right on the periodic table. Fluorine, you're absolutely right. Fluorine, if it shares electrons, it's like, I'm kind of sharing. I need these electrons as much as possible. And so chlorine and all of your halogens are pretty electronegative. So chlorine, if I draw these lone pairs, boom, 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 boom. Chlorine has three lone pairs of electrons surrounding it. It loves to have lone pairs of electrons. And these are examples of or sorry, chlorine and phosgene are both examples of chlorinated hydrocarbons. So substances that are slightly polar don't dissolve well in water, but dissolve pretty well in fats. This non-polarity allows molecules like chloroform, shown here on the lower left. So this is non-polar molecule, or this slightly polar molecule, to cross the blood-brain barrier and work as an anesthetic. So most of the times I know whenever I've seen chloroform outside of a lab, it's in a movie where someone's getting, they get, chloroform on a paper towel or napkin or something. Um, it also causes molecules to remain in fats of mammalian cells and promote toxicity within the body. Chloroform causes toxicity within the body by being metabolized to the liver to become phosgene, this compound right here. And that damages your body's defenses against toxins. So your liver takes chloroform and makes phosgene. Bad combination because phosgene, bad for liver. Or, sorry, bad for defense. So chloroform, if chloroform did not have three chlorines, it would be considered a more polar molecule, and therefore it wouldn't dissolve well in fats, and it wouldn't cause as much damage. But with these three chlorines, it's considered slightly polar. Um, okay, so then there's these class of compounds, chlorofluorocarbons and fluorocarbons. Chlorofluorocarbons, or CFCs, are compounds that contain fluorine and chlorine. They are chemically inert with most substances, and they have low boiling points at room temperatures and are insoluble in water. Thus, they're ideal propellants. So a long time ago, these used to be put in aerosol cans. So if you got like not Windex, but oven spray or something, oven cleaner, you'd spray that, and it's because these chlorofluorocarbons would be the thing that helped that solution spray out of the can. So these are ideal cans or ideal propellants in aerosol cans. However, their reactivity with the ozone results in the depletion of the ozone layer that protects Earth from harmful UV rays. Now, fluorinated compounds can be used in medical applications. For example, perfluorocarbons can be used as blood extenders and promote oxygen delivery to cells. Okay, so essentially what we've covered today so far is we've covered halogenated hydrocarbons, we've covered isomerism. Specifically, we've looked at cis-trans isomerism, and we have also looked at aromatics. So our cis-trans isomerism, our aromatics, halogenated hydrocarbons, and last but not least, alcohols. We've talked about alcohols a little bit, but I want to kind of extend that. Alcohols are organic compounds that have a hydroxyl group. Anytime you see OH, I want you to think alcohol. Alcohols can have one or more hydroxyl groups bound to the organic molecule. Alcohols are known to hydrogen bond with one another. Now, here what we have is an example of a hydrogen bond. And just to bring back bonding, we've got two major types. There's covalent bonding, which is sharing of electrons, and then non-covalent, I'm going to say non-cove. This is, I'm going to say unequal sharing electrons. And this unequal sharing of electrons takes place between different molecules. So our covalent bonding is within, so I'm going to circle this right here is a covalent bond. And now I'm going to switch colors and I'm going to circle this right here as an example of what's known as an intermolecular force. Between these two, I'm going to switch colors again, and I'm going to go with a covalent bond is strong. And an intermolecular force is typically relatively weak. So those are our biggest things. A hydrogen bond, which is the example that's underlined in red or circled in red here, is a fairly weak interaction. Now, alcohols can have one or more hydroxyl groups, so they could have multiple hydrogen bonds with them in another molecule. Alcohols are known to hydrogen bond with themselves as well as many other things. Now, let me clear all my drawings on this slide. Done. And illustrate a couple of different alcohols. We've got ethanol with 1, 2 carbons. Sorry, I see something in the chat right now. The OH, yes. Thank you very much for asking that. Let me add that in. That would be intramolecular and intermolecular here. Thank you for asking. That's a fantastic point. Great question. Okay, so we've got ethanol with 2 carbons in an OH group. We've got 1 propanol. Propanol, well, how many carbons do we have there? We've got 1, 2, 3, and then the OH. 1, 2, 3. Butanol would be 1, 2, 3, and then 4 is OH. So 1, 2, 3, 4. So that would be our butanol. Now, my numbering, I apologize, that wasn't particularly good. I started my numbering from the left. I shouldn't have, because when it comes to numbering, just like what we see with this 1 propanol, my numbering was wrong there. This is carbon number 1 because we want to give our substituent or our functional group the lowest possible number. So that would be 1, 2, 3. So these would be wrong. Sorry about that. 1 and 2. 1, 2, and 3. My numbering, I apologize, was really just to show how many carbons there are. And then this is the type of numbering that you need for actual nomenclature. This would be 1 butanol. Now, if we look at the bottom, glycerol. Okay, if we look at glycerol, I see 1, 2, 3 hydroxide groups or hydroxyl groups. And those 3 hydroxyl groups, well, it's going to be at 1, 2, and 3. So this would be 1, 2, 3. Oopsies. Actually, it would be 1, 2, 3, try propanol. There we go. So this is bringing back some of the stuff that we talked about with respect to nomenclature. And what I want you guys to anticipate before we kind of wrap up for the day is I want you to anticipate on your exam, the practice exam that I'll have up by the end of this week. I want you to anticipate questions that are like, here's a molecule, be able to answer questions about that molecule. And what is the name of that? What functional group does it have? What carbon number is this on? And so on. those are the sorts of questions that I want you to be capable to answer. In terms of prefixes and suffixes, prefixes, if you remember, most that we're going up to is 10 carbons. Um, when it comes to asking questions about different molecules, I'm probably going to keep them kind of like direct and targeted. I've been on the phone for it. Okay. I'm sorry. Okay, we'll talk in just a moment. So that's what I'm looking for us to do and what you should anticipate on your exam coming Friday. Or your practice exam coming Friday. I apologize for any alarm there. Um, but that's what I've got today. We've got some more functional groups that we're going to introduce on Wednesday. And then you've got your three quizzes that are up, as well as your your quizzes and your activities that are up. All of that's due on Sunday at 11 p.m. In the event that you missed the poll questions, I'll be posting the discussion prompt later today and posting a couple of other things later today. So just keep an eye out for that. And other than that, though, thanks for coming to class, and I hope you have a wonderful day, everyone. And I will see you guys on Wednesday. Thank you.